Hello, my name is Kyuhan Park, and I'm gonna introduce our paper Mitigating Background Shift in Class Incremental Semantic Segmentation, which is accepted in the European Conference on Computer Vision in 2024. Before presentation, I introduce you to our lab, led by Professor Japil Hall, where we focus on research in computer vision and machine learning. In the last 3 years, our lab has published 90 papers at prestigious AI conference highlighting our active contribution to AI. We have two recent papers I'd like to share. The first, published at ECCB 2024, is titled Progressive Proxy Anchor Propagation for Unsupervised Semantic Segmentation. This method introduced proxy anchors to better identify positive samples, making the model more reliable. The second, from CBPR 2024, Style Injection in Diffusion, a training-free approach for adapting larger-scale diffusion models for style transfer, developed a style injection method that adjusts self-attention features, improving the efficiency of style transfer in diffusion models. If you're interested in our lab, you can find more information through our website or QR codes. Okay, let's get back to the presentation. Now, first, let me explain class incremental semantic segmentation. The main goal is to make sure the model doesn't forget old classes when learning new ones. When the model adds a new class, it can forget what it learned before. For example, as a model gradually learns new classes such as sofa, dog, and person, maintaining knowledge of previously learned classes becomes an important goal. Let's think about a self-driving car. At first, the car was trained to recognize just cars and people. But now, we want to teach it something new, like how to recognize bicycle. Here's where a problem can happen. When the car learns about bicycles, it might start to forget what it knows about cars and people. This is called catastrophic forgetting. In the real world, retaining the car system from scratch every time we added something new takes a lot of time and money. Plus, we often don't have access to the old data that was used to teach the car before. Even if we do have that data, it's not efficient to relabel and teach everything all over again. This is where class incremental semantic segmentation comes in. The goal is to help the car learn new things, like bicycle, without forgetting what it already knows about cars and people. With this method, the car can keep getting smarter, recognizing more and more things as it goes. One of the main problems in class incremental semantic segmentation is something called background shift. This happens when the model mistakenly labels pixels from old classes like dog as background when it's learning new classes like person. When this happens, the model can start to forget the old classes, making it harder to recognize them later. This issue occurs because when we update the model with new data, we can retain it from scratch or use all the original data. So, we have to transfer the knowledge or the weights from the old model to the new ones. However, during this process, some pixels that belong to old classes might be wrongly labeled as background. As a result, the model starts to treat these important pixels as if they are not important, leading to confusion between new classes and the background. If we don't fix this, the background shift can get worse as a model learns more new classes. For example, while the model might learn a new class like sofa well, it could begin to forget the old dog class, thinking that the dog pixels are parts of the background. In class incremental semantic segmentation, the challenge is learning new classes while keeping old knowledge without using old labels. Two key techniques to handle this are knowledge distillation and pseudo-labeling. Knowledge distillation is a method used to transfer knowledge from the previously trained model to new model. This approach is widely used in continual learning to help the student model retain information about old classes while learning new ones. Pseudo-labeling is used to when we don't have the annotation for old classes anymore. The idea here is to generate pseudo-label from the previous model's predictions for old classes. These pseudo-labels act as a substitute for the real annotations and allow the new model to retain knowledge about the old classes while learning new ones. Another method is weight transfer. Weight transfer leverages the broad coverage of background class from previously trained model. The primary idea is to transfer the background weight parameters from the previous model and use them as the initialization weights for new class tokens in the update model. The background class generally captures diverse objects, making a useful foundation when introducing new classes. While these methods are useful, they often suffer from a common issue. Pseudo-labeling and knowledge distillation method rely heavily on the mold model to retain information about previous classes. Trusting to the old model too much has the result as mislabeling of pixel as background, especially when the old model isn't confident. Our approach addresses this by selectively detecting objects and ignoring mislabeled pixels during training. Although background weight transfer helps model learn new classes efficiently by using background weight parameters, it also causes background shift toward new classes. In this case, the boundaries between new classes and the background become blurred, potentially causing misclassification and confusion. So, our method addresses this crucial problem by decoupling new classes from the background through a separation objective. Our framework tackles background shift with three key components: selective pseudo-labeling, which handles ambiguous pixels, adaptive feature distillation, to focus on reliable feature transfer, and separation objective to clearly distinguish new classes from the background. In traditional pseudo-labeling, as I said before, the model assigns labels based on prediction from the old model. However, when a model comes across pixels in an image where it's not confident about the class, it labels them as background. This causes an issue where pixels that should belong to old classes are wrongly treated as background, leading to what we call background shift. This shift makes the model forget old classes because they are misclassified during training. To address this issue, we introduce selective pseudo-labeling. This method is designed to solve this problem by adding an extra step before labeling anything as background. Instead of immediately assigning unclear pixels as background, we use an ignore label for these pixels. The ignore label prevents the models from learning incorrect information from these ambiguous areas. It's like telling the model, we are not sure about these pixels, so let's not learn from them for now. First, we take the prediction made by the model for each pixel. If the model is confident about a class, it proceeds as usual. But for pixels where the prediction is uncertain, we use an object identifier. This identifier checks the combined score of all the object classes and compares it with the background score. If the score for any object class is higher than the background score, the pixel is classified as a part of an object, not a background. If the combined score isn't high enough, meaning the model isn't confident, selective pseudo-labeling assigns the ignore label to that pixel. This prevents the model from using that pixel for training and ensures that we don't make mistakes by treating pixels from old classes as background. Through this process, selective pseudo-labeling allows us to keep the labels that are reliable and filter out the ones that might confuse the model. As a result, the model can learn new classes without forgetting the old ones, which helps to significantly reduce the background shift problem. In short, by applying selective pseudo-labeling, we ensure that the model doesn't misclassify important pixels and maintains its ability to recognize old classes even as it learns new ones. Adaptive feature distillation works by selectively focusing on the most reliable features during training. To do this, we create a reliability map that helps identify which areas of images should be distilled. This map is built using three key rules. First, pixels from old classes are assigned a value of 1, meaning they are treated as highly reliable. These areas will be retained with confidence during distillation. Second, pixels from new classes or those labeled as ignore are given a value of 0. The old model doesn't yet have knowledge of these classes, so it avoids distilling uncertain information from these regions. Third, background pixels use the confidence score from the old model. Instead of treating all background pixels the same, we rely on the model's confidence to decide how much to trust these regions. This way, only the reliable background areas are considered during distillation. By focusing on reliable pixels and avoiding ambiguous ones, adaptive feature distillation helps reduce background shift and keep the learning process focused on trustworthy areas. To address the issue of background shift when learning new classes, we utilize two key techniques: label-guided knowledge distillation and orthogonal loss. Let's break them down to understand how they work together. First, label-guided knowledge distillation. When the model encounters new data, background pixels may sometimes overlap with pixels belonging to new classes, causing confusion. Label-guided knowledge distillation solves this by transferring information from the background logic of the old model to the new classes. Essentially, it guides the model, making sure that the new classes are correctly separated from the background. By distilling the refined logic from the old model, these techniques help the new model understand where the boundary lies between new objects and the background, which is crucial in preventing the misclassification of new objects as background. But that alone is not enough to fully solve the issue. That's where orthogonal laws comes in. It further ensures that the model clearly separates the new classes from the background by making the new class weight orthogonal, or independent from the background weights. This creates the clear boundary between the new classes and the background, preventing overlap and confusion. By forcing the new class representations to be distinct from both the background and the old classes, orthogonal laws ensure that the model doesn't mistakenly blend old and new information. Together, these two methods, label-guided knowledge distillation and orthogonal laws, works in harmony to reduce background shift toward new classes. Label-guided knowledge distillation transfers essential knowledge from the old model to the new classes, while orthogonal laws make sure that the new classes are clearly separate from the background. This combination ensures that the model can accurately learn new classes without losing the ability to recognize old ones. In our experiments, the scenario involved learning initial sets of classes, such as 19 or 15, followed by incremental learning of 1 to 5 additional classes at a time. The overlap settings include both current and future classes, increasing the challenge, while the disjoint setting includes only current and past classes. Despite the difficulty of the overlap setting, our method achieved state-of-the-art results, especially in the 50-to-1 overlap settings scenario. Our approach consistently outperforms others, including our superior handling of incremental learning. The ADE20K dataset presents a much more challenging scenario than Pascal VOC, with 150 classes compared to Pascal's 20. Despite this increased difficulty, our method still achieves state-of-the-art performance. This is particularly notable in challenging multi-step scenarios, such as the 50-to-50 and 100-to-5 settings. Our method handles both large and small incremental class learning effectively, proving its robustness and adaptability. In this evaluation study, we explore the impacts of the selective pseudo-labeling strategy on class incremental semantic segmentation. As you can see from the comparison of pseudo-label map and selective pseudo-labeling map, selective pseudo-label significantly improves the model ability to avoid mislabeling background pixels. The table is the ignored label ratio as training progresses across steps. Selective pseudo-label consistently identifies and filters out around 37% of misclassified pixels on average. This shows that selective pseudo-labeling helps reduce the background shift. And second evaluation study demonstrates the effectiveness of the orthogonal objective in reducing background shift. On the left, you can see the baseline similarity between background, old classes, and new classes. The baselines show high similarities of 91% between background and new classes and 91% between new classes, leading to background confusion. On the right, our method reduced these similarities significantly. This clear separation shows how the orthogonal objective helped to isolate new classes from background. In this qualitative analysis, we compare our method with a previous model and a baseline that used traditional pseudo labeling and distillation techniques on the Pascal VOC 50-1 in overlap setting. The results showed that our method significantly outperformed both approaches in retaining knowledge of older classes while learning new ones. Notably, our model consistently produced fewer misclassified pixels compared to the baselines, demonstrating superior performance in challenging scenarios. Thank you.